My name is Sahil Khose, and today we'll be talking about the paper CycleGAN. The title of the paper is Unpaired Image-to-Image Translation Using Cycle-Consistent Adversarial Networks. And before we get into CycleGAN, we'll just discuss a bit, like a quick summary about what GANs were, and then we'll move on to this paper. I'm hoping that this summary is shorter than what we have had before on this channel because of the simplicity of what this paper does, and yeah, it's a very well written paper altogether. So before, as I mentioned, before we get into CycleGAN, we'll just quickly review what GAN paper did. So GAN paper came out in New Year's 2015 by Ian Goodfellow and others. And what essentially the paper did was that it proposed, so in 2012, after AlexNet, classification models using deep learning got very powerful, and generative models could not catch up. So because inherently generative modeling is so much more difficult task than what classification would be, right? So what the authors of this paper proposed that let's just use this powerful discriminator classifier to train a generator, right? So how can we exploit that? They suggest two models which are trained in a minimax type of optimization, which is generator and discriminator. And if you go down, you'll be yeah. I think this diagram will confuse. Yeah. So both discriminator and generator. So the generator would be a model that takes in a noise vector as input, and then it generates an image, and that image is considered to be generated or fake image, and the actual distribution of the data that we're trying to map through this generator is the real image, and the discriminator is a binary classifier which classifies whether an input image is real or fake. And that's how this min-max optimization is, that the discriminator, when it gets a real value, so discriminator wants to be better at discriminating real and fake images, and generator wants the discriminator to fail at doing so. So in this optimization, discriminator has to get better at recognizing the finer details of what differentiates between a generated image and a real image, and generator, to optimize for this problem statement in the best case scenario, will have to come with better generated images so as to fool the discriminator and hamper its performance as much as it can. So that's what is represented in this image. On the left side, you can see Z, or the noise vector, is mapped to X. X is the data distribution that we are trying to map through the function g of Z, and g of Z would be passing your noise through the generator, and the green color right over here, yeah, the green color distribution is the fake image distribution. The dotted one, or in the black, is the actual data distribution that we are trying to map using this generator, and discriminator is trying to differentiate between both of these distributions, right? So from A to B, you get a perfect discriminator after you train. First you train the discriminator, because we need a good enough discriminator for the generator to start training, and once you get a perfect discriminator, so in this image B, what the discriminator is trying to the dotted line in blue is the average. So it's just the sorry, not the average, it's the ratio between the values of this both the data distributions. And as you can see, it yeah, when both are equal, or even this is 0, so the sorry, my bad. The discriminator is just trying to differentiate between both these distributions, and when you train the generator comes as close as possible to the data distribution and shifts to the left. And in the optimal case, the discriminator does not know how to distinguish between a generator and the generator and the discriminated. So in this scenario, this probability value is 0.5 because it completely, so it just basically random outputs or predictions, sorry. In this case, because this is original data, this predicts 1 which represents real, and fake is represented by 0. Hence, as you move towards the green distribution, which is the generated distribution, this discriminator value starts going down, because 1 represents its prediction value, which is real. Hence, when it's a perfect discriminator would have a curve such like this. All right. So given that we have gone through this idea behind how GANs work, we'll hop on to CycleGAN. And what CycleGAN, so there is a very famous example which is popular when we talk about CycleGANs. It is the diagram of zebras and horses. Let me just zoom in a bit. Yeah. So what happens between these images of zebras and horses, what we are trying to do through this image to image translation, as you can see in the title, is unpaired image to image translation. So what that means is you want to translate a particular image, but in this particular scenario you want to transfer the image of a zebra to an image of a horse, and both of them look very similar, but apart from the obvious difference in texture, obvious difference in color that they have, the color pattern that they have, right? And you can see other pairings as well, from summer to winter. So in winter you'll see that there is more snow, and yeah, there is not much greenery around. Similarly, here you can have like a lot of such paired images, more native photos, right? And you can also have different styles of the same painting, by the Van Gogh's starry painting. So that is one, or probably Van Gogh style of painting pictures, right? So you want to translate these images into a new style, right? So this would be an image to image translation task. And how we solve this using generative adversarial networks in CycleGANs is something that we'll be focusing on as well, right? So yeah, so as we looked into how GANs work. So given an input z, there will be a generator which will produce the data distribution g of z to map the data distribution x, and discriminator will be trying to distinguish between this x and g of z, right? So that is the singular optimization that what was proposed in GAN, the paper GAN, and we'll be using a similar concept of generative adversarial networks here, but with more complexity. So what we want is, we want x. So x in this case is the image from domain 1, which would be, we'll just stick with the example of horse to zebra in the following discussion. And the x over here would be the image of a horse, y over here would be the image of a zebra. Now you want to translate this image x of a horse to a zebra. So you will need a generator which generates the new image, right? And it also takes in the input image. So what happens is you have this generator G which translates this image X to image Y, and you have another generator as well in this architecture which translates the image Y, so the image of a zebra, back to X, that is the image of a horse, right? Now when you just look at it in one direction, when you have generator G, what do you need for optimization for generator G? It does not have any loss of its own, but it's propagated by the loss of the discriminator. So this generator G will be optimized with the help of the discriminator, that is discriminator Y. This is called dy because it tries to distinguish between g of x and y, because g of x is trying to model y, the domain y. This would be discriminator y. Similarly, you have discriminator x, which is trying to recognize the difference between f of y and x, right? So having cleared this up, that just to recap, we have two generators g and f, and we have two discriminators dy, which is helping the generator g, and dx, which is helping the generator f to learn better representations, right? Now there's one important thing. If you go back to the title of the paper, it's called unpaired image to image translation, right? So why was CycleGAN paper so important when it came to image translation? I think we can go to my notes over here. Image to image translation can be done using autoencoders pix-to-pix networks and CycleGAN. CycleGAN was developed later after CycleGAN. So, and an autoencoder, you will basically have MAC loss over the input image and the output image, or free. When this is paired, an autoencoder, the output of the autoencoder will have its paired y. So the y hat will have its paired y, so as to propagate the loss. So one easy example would be that you have an image that you want to map it to a segmentation map, right? And for the segmentation task, you input into your autoencoder the image that you have, and then you'll expect the autoencoder to generate the segmentation maps, right? Now, in such supervised scenarios, you will have a segmentation map generated by a human being, which will be used as a label for this autoencoder to train on. So this data is paired because pixel by pixel, it is similarly like the output that you have that is generated by the generator or your model has a exactly paired label that you have. But when it comes to image-to-image translation in unpaired, CycleGAN was one of the first successful papers that came out for this translation task in an unpaired manner, which says that the new domain task, the new domain that you're generating the images in, you should not have exact pair, because it's very difficult if you have like images of horses and images of zebras. It's very difficult that both of them are in same poses, same background conditions and all of that, right? So image-to-image translation unpaired would be like you just have a bunch of images of horses and bunch of images of zebras, and you're just trying to map it. Use just these data distributions to map one data distribution to another through these generators, right? So CycleGAN came in. Generator objectives were as follows. So the translated images look like a zebra. So if we consider the generator G, it will be the objective for its generator is to translate the image which looks exactly like the zebra. So this uses a discriminator to achieve this task, right? Now, what happens is this could lead to a lot of problems, including mode collapse, as it might just produce the image which is barely able to fool the discriminator, and both of them won't optimize and it might also just lose the information completely, and it could output things that are just fooling the discriminator and are not actually making learn to represent the distribution better, right? So what we need is once we convert this image of a horse to a zebra, we need that this new image that is generated of a zebra, it should have enough information that it is again translated back to a horse, right? So that's the second generator objective. It's like translated images looks like the original image, so you translate it back and it should look like a horse, right? So this is why you have two generators going back and forth, G and F, and you have two discriminators to optimize both of them. On top of it, there is there is cycle consistency loss, which they have introduced, and which is able to produce excellent results when it comes to the ablation studies. We can see how the performance is without the cycle consistency loss, and how qualitatively the results get better just because of the introduction of this, right? So going back to the losses, we went through figure 3a. Now going to the figure 3b. So your G is converting your X domain horse to G of X would be Y hat, and the Y that the discriminator, so dy would be the discriminator. The discriminator will be training on Y hat and Y, so the images from the Y distribution, right? And now you'll take this Y hat, you'll take this Y hat that is generated by this generator G and pass it through your generator F, and then it will produce X hat, right? When it produces X hat, it should look similar to X. Hence, you'll have the cycle consistency loss where you have this X, you translate it to Y hat, then you take this Y hat and translate it back to X hat, and now you will have MAC loss on this, right? Because they should be as close as possible, and the optimization of a discriminator will be completely different. This will be the discriminator will be trained on Y hat comma Y, and the same discriminator loss will be propagated to G as well, right? Okay, so this is one part. Okay, so X to Y back to X hat, X to Y hat back to X hat, and these two should be as close as possible in the space. Now going back, what if we start with the image of zebra instead, right? Z, Y. Then it is translated to X hat, then to a Y hat, right? So we start with Y, X hat, Y hat, right? And these should be as close as possible. Hence, the cycle consistency loss is applied over here. Right. Now we'll go to the equations. Cycle consistency loss wasn't proposed by this paper, but it was used by this paper to solve this image-to-image, unpaired image-to-image translation task. So the normal loss that we will be using for both G, so this is just for generator G, you'll be having your adversarial loss for GAN, right? And you'll have a similar one for generator F as well, but then you'll have also another loss, which is cycle consistency loss, which is G of X. So this would be Y hat, this would be Y hat, passed into F would be X hat, and X, the distance between X and X hat should be as small as possible. Plus the other way around, also the C section that we saw in figure 3, F of Y would be X hat, and G of that would be Y hat. So given Y, we go to X hat, then we go to Y hat, and Y hat and Y should be as close as possible. So this cycle consistency loss that these guys introduce in this architecture, and this is the final loss, the adversarial loss of generator G, adversarial loss of generator F, and the cycle consistency loss with a lambda, which they I believe is 10 that they're using here, right? Yeah, so lambda is equal to 10 is used, Adam is used with batch size of 1, because these there are so many models like 2 generators and 2 discriminators at play here. It will take a lot of compute for you to manage all the gradients and then do back propagation. Hence batch size of 1. I assume that was the constraint for batch size of 1, because it is not optimal for you to have smaller batch sizes, especially in generative training of generative adversarial networks, right? Another very peculiar detail that is very interesting to look at. So ever since GAN, a lot of new papers came in where they developed a lot of tricks for training these GANs or large models in a very efficient manner. One such paper was patch GANs. So for the discriminator in the CycleGAN, they used 70 by 70 patch GAN introduced discriminator, which aimed to classify whether a 70 by 70 overlapping image patch are real or fake. So instead of boiling it down to recognizing if the entire image is real or fake, you just make 70 by 70 grids over the image. After you pass through a discriminator, you will get a representation of actually a 3D representation, depending upon how many filters you have. But you have a representation, and then you slice it into 70 by 70 image patches, and then you classify every single patch if it's real or fake. Now this reduces the number of parameters dramatically, and also it helps to fit these huge models. So it's not just like the one model is huge, but you have so many models that it allows you to train more efficiently. And they replace the negative likelihood loss objective by least square errors. And yeah, so this is basically the model architecture that we saw, and the implementation that the small patch GAN technique of 70 by 70 in their discriminators. This was a novelty that they have added as well. So you will have the PyTorch and Torch code. So all the links will be mentioned below in the description. Yeah. So one thing that is very interesting when it comes to GANs or any generative models is that the evaluation metrics are very subjective and not so they're not refined, and you won't be satisfied with the metrics that we have, because it is very hard to quantify how good a generator or a generative model is, right? So few of the evaluation metrics that they have used, we'll just look through them and see what's interesting, right? So they use Amazon Mechanical Turk perceptual studies, where humans are assessing how real an image looks like, right? And so they compared these metrics with a lot of different architectures, including BiGAN, CoGAN, feature loss GAN, SimGAN, CycleGAN. So this is their output. Pix2Pix, which was also the paired image to image translator model, which came around before CycleGAN. the ground truth example, right? Now, as you can see in CycleGAN, or if you compare the output, the task over here is to just translate this particular. So if it's a aerial shot, then you have to translate it to its corresponding. Just the grid of the street, and if it's just the grid of the street, then you transfer it to a aerial image, right, by satellite image. Now, when this happens, so the generator has to do both the tasks, right, from x to y and y to x, right? So when you have this input, you can see most of the models are generating this new domain, right, or something different. But CycleGAN is not. CycleGAN is retaining what it had as input in all the 4 examples, right? Now, what would be the issue? The issue is the CycleGAN was specifically made for making minor adjustments or smaller changes in style from a particular image to the new generated image, right? So that's what it's trying to do, and that's what it was optimized on. It was not optimized on completely changing the domain of the input data, right? That's why we are able to just see that it's mostly passing through all the information and removing or adding some details there, because that's what it was optimized on. And the argument that we had during our discussions were that this is kind of unfair because CycleGAN was the only one which was trained on unpaired image-to-image translation tasks. And as you can see, pix-to-pix, not necessarily you'll see in this image, but what they had observed is that pix-to-pix, because it was like a pair-to-pair trained model, it had higher resolution when it was trained on such data sets, because you did have paired images here, right? So even though CycleGAN was amazing at its performance when it came to unpaired images, but pix-to-pix was superior during such evaluations when you compare it against CycleGAN. So this is figure 7. We'll have the study when you have the ablation study of different kinds of losses that were applied for this training purpose. So this is on the leftmost you'll find the input, rightmost you'll find the ground truth. This is the CycleGAN output, and these are slowly you're adding different components to the CycleGAN, right? Now, if you just have CycleGAN loss, cycle consistency loss alone, you'll get this output. Now, this is not very good because only you don't have the adversarial losses that you don't have any kind of adversarial losses. What you're just looking at is when you're transforming from x to y hat to x hat, x and x hat should be as close as possible. Similarly, for the y to x hat to y hat, y and y hat should be as close as possible. That's all. So the generator struggles a lot while doing this task. Now, what if you just have the adversarial losses, like the first two, LGAN G and LGAN F, right? You'll see that the results are pretty good, at least compared to when you just had cycle consistency loss, right? Now, cycle consistency is of 2 methods. There is a forward cycle consistency loss, which is the first half of the equation, and the backward cycle consistency loss, which is the second equation, right? Now, what you can observe here is GAN forward, when the input image when the input is the image and it wants to generate the segmentation map, GAN plus forward is performing nice. But when you look at GAN plus backward, that it does not have the forward, it just has the backward. So what it is trying to map is that, okay, given that you have images, segmentation images, you want to produce this and this here. Given that you have the segmentation map to begin with, you should be able to generate the input image and then back to the segmentation map. What happens is it's not able to do that good of a job. But when it has, when you select that your first domain 1 is a segmentation map, now the task will be inversed. Now you'll have to start with an image, translate it to the segmentation map, and then come backward. Sorry, we are looking at this right now, right? Come back to, come back to the original image, right? and this looks better. This and this, the ground truth over here, this and this looks like actually better than what we look at here. Now the hypothesis is that these segmentation maps that are generated, which are represented here, these have very less information to begin with, right? And if you use that as a starting point, it will be very difficult for you to generate newer details to create this image, right? And then coming back to the segmentation map, because you already did not have good enough image, sorry, you did not have good image to begin with. Because of the information loss, you're not able to produce as good when you look at this. But when you start with an image and then move to a segmentation map, it seems like you are like that would be a better task to do. So that's what it's being reflected in GAN forward and backward. Finally, when you add all of them together, the final CycleGAN will perform very good. Although it is still like a lot far away from the ground truth, but it is better than everything that we saw together. So this is just a justification of every single loss that was used, right? And you can see, so this paper is very nice in this, in the sense that it has a lot of images for you to actually qualitatively see how it is. And yeah, so the limitations that they discuss, and now I'm just coming to the end of our discussion. One limitation that they discuss is that when you're using this for smaller adjustments in the domains, then it performs well. But when it comes to, so like you can just see here, so tasks that involve color and texture, it is performing very well. But when you go for a more difficult task, like let's say the geometric changes are there, and yeah, a lot of things are changing. So like, for example, dog to cat transfiguration, not just this model, but every model around this time was failing, and even this model is no exception to that, right? Because it's a much harder task to optimize on. And yeah, here's just a bunch of images that you'll see, and they're actually very good if you look at them very carefully, right? So outside of this, as we saw earlier last Sunday when we discussed the VIT paper, we are also trying to implement allocating 2 hours for us to try to implement the paper idea or the architecture as much as we can to get a better clarity. We do have the repo for this as well. Let me just pull it out. Yeah, it's again in the same repository, noob speedrun, Adityakani 2001. The link for this is also in the description, and we've just written the model that we, so the model, let me just pull up the paper, one sec. Yeah, the implementation detail is down in the appendix, right, yeah, here, the training details and the network architectures. So we've implemented this generator bit and the discriminator bit along with the losses, and you'll find this class C7S1K with there, DK, UK, and again the CK over here for this final model, right? And this is the final model as well, using C7S1 C7S1K, DK, and RK, right? Let me just pull up the repo. Yeah, so you'll see you have implemented C7S1, D, then R, and then used all of them together in generator, right? And then we have CK for the discriminator itself, and a code to check all of that. And then in train.py we have the losses as well. So the final loss will have the GAN G loss, the GAN F loss, and the cycle loss into lambda. That was used as 10, and then we just check if everything is working fine. So I encourage you all to go and check it out, and if we'll be posting up issues if anyone wants to contribute to that, and if you have any suggestions, please let us know below in the comment or in a repo. If you have some issues, you can just put it online. Let me just before going, let me just check if everything's all right. Yeah, I think we covered everything. So thank you everyone for joining in. I'll see you in the next one.